What's up, Math 104? Here we go. This is your second online lecture video. Look at that, I already made a mistake. Shoot. Okay, this is your second online lecture video. What are we doing today? We are in section 7.1. Now, I had y'all watch a number of Khan Academy videos, and this video is just an accompaniment to those videos. Check out that dude, Salman Khan from Khan Academy, the dude Teleboss. I'll talk more about him in the Zoom meeting tomorrow. What are we doing in section 7.1? We're going to be talking about inverse trig functions. What exactly are inverse trig functions, and what exactly are inverse functions in general? Consider the following. Remember way back when, chapter 2, we talked about functions? You can view functions as maps. In one set in the green here, we'll call that the domain. I've got this machine, we'll call it F. I put x's inside it and the outputs are y's. Now, you can view this F as a map, right? Mapping things in this set in green to this set here in gray. Now, what about a map going backwards? Is it possible to find a map that will take the things inside this gray set and map them back to this one in green? We've been dealing with functions and their inverses basically your entire life, right? I mean, consider the following. You probably have a social media account somewhere. And how does this thing work? Well, you have a unique username and password. This is like a two-variable function, right? You input a username, you input a password, your output is your social media account. Is there a map that goes backwards? The answer is obviously yes. So obviously the people that own like Facebook, for example, they can take a look at your account and they know how to map that back directly to your username and password. So functions and their inverses are pretty important. They come up quite often in the real world. Now let's talk about how they relate, how they come up in trigonometry. First off, I need a condition here for when we have this map going backwards. You do not always have this map going backwards. A function f of x has an inverse function denoted by f to the negative 1 of x if and only if f of x is a one-to-one function. What exactly is a one-to-one function? We're going to get to that in a bit. So you have a map that goes backwards if and only if the original function is a one-to-one function. And for this map that goes backwards, well, because the map goes backwards, the domain and range of the original function, they end up becoming the range and the domain, respectively, of the inverse function, as I have written here. So you have that a function is one-to-one if and only if it has an inverse function. What does it mean for a function to be one-to-one? There's quite a number of things here involving one-to-one functions that are skipped in this class. Don't worry, you'll see them again in pre-calculus. A real valued function is one-to-one if its graph passes the horizontal line test. So in this class, we only deal with functions whose inputs and outputs are real numbers. You have that a real valued function is one-to-one if its graph passes the horizontal line test. Well, what's that? Horizontal line test states the following. For every horizontal line drawn, the line touches the graph at most once. Let's look at two quick examples. In the black, I have drawn for you two functions. The first is x cubed, the second is x squared. I've drawn a few horizontal lines here. In the first example, now bear in mind the horizontal line test needs to be satisfied for all horizontal lines. But it's clear to see from the graph of x cubed that no matter what horizontal line I draw, x cubed will be a one-to-one function, whereas x squared is not. If you draw a horizontal line that goes through anywhere on x squared, anywhere that doesn't go through that vertex there, you're going to touch the function in at least two places, right? So the function x squared is not one-to-one. These are not rigorous explanations for why these functions here, at least for x cubed, it's not a rigorous explanation for why it's one-to-one, but we're not going to get into that. Now, clearly, you look at the graph of the sine function, assuming that you continue to graph the entire sine function, not just for one period, but throughout the entire domain of sine of x, which would be all real numbers. This graph is not one-to-one, right? Let me just choose a color here and draw a horizontal line. I mean, clearly, if I draw a horizontal line, that's going to cross the function in infinitely many places, right? Now, here's how we can make the graph of sine of x. We can take, how we can make it a one-to-one function. We can take the graph of sine of x, and we can restrict the domain of sine of x. If you restrict the domain of sine of x, well, then you end up having to erase a bunch of parts of the function. Let's suppose that I restrict the domain of sine of x so that instead of looking at the domain being all real numbers, I look at the domain just being between negative pi over 2 to pi over 2. Seems like an odd choice. Why did I choose these values? This is typically the convention for restricting the domain of sine of x. If you restrict the domain of sine of x in such a manner, the restricted domain will just be one interval, and the outputs of the sine function on this interval will be the usual range of sine of x that we are used to working with, the range being from -1 to 1 inclusive. So now, with this restricted domain of sine of x, I have sine of x as a one-to-one function. Why do we care? With this restriction of sine of x, we now have an inverse function for sine of x. That inverse function is denoted by sine to the power of -1 of x. This is called the inverse sine function. It is also referred to as the arc sine function. In those Khan Academy videos that I had linked in Canvas, Salman Khan refers to all of these inverse functions as arc sine, arc cosine, arc tangent, respectively. They are also called the inverse sine, inverse cosine, and inverse tangent. Remember how the inverse functions work. The domain of the original function becomes the range of the inverse. The range of the original function becomes the domain of the inverse. This is extremely important and vital for understanding the outputs of the inverse sine function. Let's talk about why. The range of inverse sine is from negative pi over 2 to pi over 2. Now, before we even take a look at some problems involving inverse sine functions, involving inverse sine, let me remind you something extremely important when it comes to trig functions and their inverses. With trig functions, my input is an angle, my output is a ratio of two sides of a right triangle. Sometimes the end result is simplified. Sine of pi over 4 is root 2 over 2 divided by 1, which simplifies to root 2 over 2. Another example would be tangent of pi over 4. Tangent of pi over 4 is opposite over adjacent. Look at that right triangle. You have root 2 over 2 divided by root 2 over 2, which simplifies to 1. Yeah. So once again, with my trig functions, I plug in an angle. My output is a ratio of two sides of a right triangle. Which two sides those are is dependent upon the trig function. Now remember how inverse functions work. They are maps that go backwards. The way your inverse trig functions work will be as follows. The input of an inverse trig function is a simplified ratio, sometimes simplified ratio, of two sides of a right triangle. The output of an inverse trig function is always an angle. That angle must always lie within the range of your inverse trig functions. So consider this problem here. Sine inverse of root 2 over 2. What does this equal? Remember, the output of an inverse trig function is always an angle. The range of sine inverse is from negative pi over 2 to pi over 2. I have drawn that range for you here on the bottom left. The angles that are within the range of sine inverse, they are angles in quadrant 1 and in quadrant 4, but these are not all going to be positive angles. You have angles ranging from negative pi over 2 to pi over 2. So sine inverse of root 2 over 2, you need to ask yourself this question: sine of what angle equals root 2 over 2? Well, you know that that's a unit circle value, right? Sine of pi over 4 is equal to root 2 over 2. And so inverse sine of root 2 over 2 is equal to pi over 4. Remember that your outputs of your inverse trig functions, whatever you write down, you need to make sure it is within the range of the inverse trig function. So let's take a look at this next problem. What is sine inverse of negative root 2 over 2? Perhaps you take a look at this at first and you ask yourself this question: sine of what angle equals negative root 2 over 2? And you say, oh, looking at the unit circle, sine of 3 pi over 4 equals negative root 2 over 2. That is a true statement. So perhaps you write down that sine inverse of negative root 2 over 2 equals 3 pi over 4. But this is wrong. Why? Let's draw this angle of 3 pi over 4. That angle is in quadrant 2. That angle of 3 pi over 4 is clearly greater than pi over 2. It cannot be inside the range of sine inverse. So you need to find another angle that is inside the range of sine inverse so that sine of that angle equals negative root 2 over 2. Remember, the range of sine inverse is from negative pi over 2 to pi over 2. This angle of negative pi over 4 is inside the range for sine inverse. That angle of negative pi over 4 is in quadrant 4, and it's this guy right here. So our answer to this question then is in fact negative pi over 4. Let's look at another problem. Sine inverse of 1 is equal to something. So this is equivalent to asking sine of what angle equals 1. I'm going to say this again. You know I'm going to say this a lot throughout the semester. The way my trig functions work, I plug in an angle. My output is a ratio of two sides of a right triangle. The way my inverse trig functions work is I plug in a ratio of two sides of a right triangle. My output is always an angle. The output of your inverse trig functions are always angles. So sine inverse of 1 is pi over 2. Pi over 2 is in fact inside the range of sine inverse. So this is our answer, and it's circled. Let's look at one more of these problems, because that's all I got time for here. Sine inverse of negative 1 is equal to what exactly? So remember, output of an inverse trig function is an angle. This is equivalent to asking sine of what angle equals negative 1. Perhaps you write down that sine inverse of negative 1 equals 3 pi over 2, because sine of 3 pi over 2 equals negative 1. But this is incorrect. Why? Let me draw this angle 3 pi over 2. That angle is in quadrant 3. It is clearly greater than pi over 2. This is not going to be inside the range of sine inverse. Your range of sine inverse is going to be these angles here in quadrants 1 and 4. The angles in quadrant 4 are negative. The angles in quadrant 1 are positive. I need to find another angle that is coterminal with 3 pi over 2 and is inside this range of sine inverse. And clearly that angle of negative pi over 2 is coterminal with 3 pi over 2. It is also inside the range of sine inverse. And so our answer is negative pi over 2. All right, y'all. I hope this video was worthwhile for you. This is my second video here, and yeah, I don't know how to end this. Okay, bye.